Hello everybody, my name is Stefan Bosse. I'm a private lecturer and senior researcher at the University of Bremen in the departments of mathematics and computer science, and today I want to give a talk about surrogate predictive and multi-domain modeling of complex systems by fusion of agent-based simulation, cellular automata and machine learning. Okay, first of all I want to give a short introduction. What's the topic of this work? Now, most of all, it's modeling and simulation of complex dynamic systems with respect of societies, large-scale population, and so on. And here in this work, we use the case of pandemic outbreaks. Other use cases are traffic flows in cities, like the smart city context, and so on, crowd flows, and so on. So we want to derive on macro level so-called aggregate variables, observables, on a macro system level, from analytical models and simulation on micro level. So we want to model and to simulate on micro level and to get observables on macro level. We want to perform prediction of time-dependent aggregate variables by a combination of machine learning and simulation. And finally, we want to perform a coupling of simulation with real-world environments, including digital twin methodologies. This is not part directly of this presentation here, but it's an important methodology that we are using. So what are the issues? First of all, a high variance on entity micro level. That means interaction of people with traffic control, with domestic vehicles and so on, or between humans, and most of all, unknown and or incomplete entity interaction models. So entities are here mostly humans. So secondly, we have a lack of sensor and model calibrations, affecting functional modeling and simulation too. Another issue is the accessibility of real-world sensor data. And we have a high dimensionality, size, and distortion. That means bias, test coverage, test strategies, skewness of distribution, and so on, of real-world data. So finally, we have a high number of micro-level entities in simulation to get a reasonable statistical strength. To have representative simulations, you need thousands, maybe millions, or 10,000s of entities to simulate, for example, a pandemic outbreak. So we have the issue of computational complexity and time. So we are here addressing in this work basically 2 of 3 modeling levels. First of all, what's the most interesting level here, but not directly accessible commonly, is the macro level. That means the description of the system behavior with aggregate variables, the so-called observables, of such large-scale ensembles, like millions of people, computed typically with analytical functional models derived from real-world observations and experiments. So this is the system level, and based mostly on statistical methodologies. Secondly, we want to address the micro level. That means modeling of complex systems by micro-level entity behavior and interaction together with observation of macro-level system behavior. That means the derivation of aggregate variables by simulation and test, by probing in a simulation. So we have a modeling on entity level, the interaction of humans, the mobility of humans, the behavior of humans, and so on. And we want to observe the emergence of the ensemble. That means the macro-level observables. So here we're using basically multi-agent modeling and simulation. Yeah, and finally, there's the meta level, or here I call it meta level, the description of micro and macro level behavior, not based on direct observations, and this is typically big data analysis. This is not performed here, although data mining is another part of our work, but not addressed in this work. So there are different methodologies already introduced. First of all, the functional modeling. This is not addressed here in this work. We address simulation. The functional modeling, typically known from social science, for example, or economics, basis on mathematical models, parameterized mathematical models that are created by observations, developed and evaluated by observations, and finally applied again to observables. We want to use simulation, basically agent-based simulation, and simulation can be used to probe system observables from a large set of interacting micro-level entities, in this case, in real world, humans, in the simulation world, agents. Then we have static data modeling. That means supervised machine learning is used to approximate and develop the mapping function that is originally described by a closed mathematical model. But here we use an approximation. It's not the same, it's a hypothesis of the unknown model function f that maps input variables like sensors to observables. For example, the mobility of people has an impact on the infection rate in a pandemic outbreak. So here we use an approximation by supervised machine learning to approximate this unknown model function. And finally, we have dynamic data modeling. That means machine learning is used to predict the future development of time series data and, of course, the desired observables. Why? For example, I know the history of the development of the weekly infection rates or infection cases in a pandemic situation. Then I can predict the future development like stock courses. So modeling and simulation is an important part here, and the combination of machine learning and simulation can improve model and simulation quality in different ways. First of all, machine learning assisted simulation improves the simulation model and quality. Secondly, simulation assisted machine learning improves the prediction or a classification model. Thirdly, this is here the main topic in this work and in this presentation, emulation of multi-agent systems computed in simulation by an machine learned macro level model, the so-called surrogate modeling. So I have an ensemble of interacting interentities. I can perform a simulation. This can be very time consuming. And then I derive a surrogate model that replaces this large-scale system by one statistical approximated averaged model. And finally, machine learning can help to calibrate sensors, both in simulation and in real world. The most significant issue in modeling is that the real world data is not calibrated. They are not sensors. For example, population data is highly distorted. There's a bias, as already mentioned, and so on. Okay, so we propose here a hybrid methodology. And already said, the major issue with real-world coupled simulations and predictive machine modeling from simulation is the discrepancy of sensor data, both input and output observables, collected in real and in simulation domains. And this is the main issue. So we propose a hybrid approach combining multi-agent system simulation or multi-agent-based simulation with cellular automata, with probabilistic cellular automata simulation for reasons of efficiency. Agents and cellular automata are very closely related, but a CA model is much more simpler and can be computed much more efficiently and scales well better due to totally different range of communication of entities. In agent systems, there is no limitation. In cellular automata, there's typically a neighborhood relation of communication. This is the reason why a CA performs much more better than a agent-based system. So we use agent-based simulation, cellular automata combined. The way we do it, I explained later. And we incorporating real-world data for the parameterization of the simulation world and the agent modeling, including the cellular automata. We use a digital twin concept. This is not explained here, but it's part of our work. And the digital twin concept means we use real-world data to create agents in the simulation world, but related on data from specific entities in the real world. That means, for example, we're performing a survey, a micro-survey, and humans answering this survey, and we can derive parameters of the behavior model of agents. This is meant with the digital twin concept. Yeah, and finally, prediction of future developments of system state observables from past data. Then, beside this hybrid multi-agent simulation, cellular automata simulation approach, we have a hierarchical domain-specific simulation approach and a decomposition with respect to longitudinal and spatial scale. That means agents represent special domains, for example, towns in a country or so-called terrestrial units. And these agents controls a cellular automata. And this cellular automata simulates, for example, humans in a town or in a sub-area of a town and so on. And the cells of the cellular automata represent individual entities in this special domain. And finally, we use predictive modeling of time series data of aggregate variables using state-based machine learning models, trained on one hand by real world and on the other hand by simulation data. So simulation augments or replaces real world data. Augmented data is used to train predictive models, for example here in the use case infection rate development. We have sequential time series and sequential time series predictive models for surrogate observable variables with typically auxiliary sensor variables. And we have models that are applied to real-world data, predicting finally real-world observables. And this is the roadmap, the far away goal, that we can train machine models in simulation that can be applied to real-world data and delivering some meaningful prediction, classification, or time series prediction of real-world observables. It's actually not, of course, not really possible. It's difficult. So we have actually a gap between real world and simulation. But we try to narrow this gap to make it smaller with the contribution of this work. So here the basic concept of the agent-based simulation. Here we have the real world on the left side, and with a lot of entities, not only humans, we can have machines, vehicles, buildings, and so on. So the interaction is not limited to from human to human. It can include a human-machine interaction and so on. So then we have sensors, either local sensors or also sensors on micro level or sensors on macro level. And finally we transfer, especially with the concept of digital twin methodologies, the behavior of humans, for example, to agents, very simplified in common. And so we have an interaction of agents in the simulation world by performing agent-based simulation. And of course, we have again sensors, agent sensors for the micro level observations. And we can, of course, compute any macro level observable. For example, the total number of infections in a pandemic situation. This cannot be computed here in real world. Well, it's measured in real world correctly. Yeah. Because the number of infected people are unknown, typically. there are tests, test strategies, there's test probing that is changing over time and in the horizontal and vertical axis. So again, here we come back here to the simulation. We have a micro model, typically modeling the behavior, interaction of humans, the mobility, decision making, and so on. And we have a macro model that is unknown. And the main issue with simulation, you don't know the macro model. You don't have a macro model. You can observe the outcome of an unknown macro model by accurately. There's high accuracy, 100% accuracy to observe some or to measure some observation. But this is only by test and probing. Okay. So here is our overall architecture. Here, the first thing we here left, you have the real world, and we derive real world data to parameterize and to model the simulation world. And the simulation world consists firstly of domains, of spatial domains. So with the partition, the entire simulation world, or the real world, for example, the country Germany, in domains, for example, terrestrial units, basically towns and larger areas around towns. And then we have an agent that's responsible for one domain to finally control a cellular automata that performs the real people behavior, interaction, crowd, ensemble, interaction, and the behavior of the entire crowd and ensemble. So we have agents that control, that are responsible for one special domain, and they are responsible to collect the observables. For example, in the pandemic situation, the infection cases. And here we have the cellular automata that is further partitioned in sub-areas, for example, working area, school, shopping, and so on. So this is the basic concept, and the second part is the time series prediction by sensor data, past sensor data, to predict future outcomes of observables. Okay, this is the basic architecture that they are using, the specially partitioned simulation world. Each partition, each special domain is represented and controlled by an agent. And the agent can interact, for example, if people cross domains, for example, leave one domain and enter another domain, for example, traveling to other countries and so on. And this is handled by the agent, and the agent collects the observables, the system observables, and so on. And he controls the cellular automata. So we are using machine learning, and the aggregated data collected from simulation is used to train a surrogate machine model for time series prediction. A state-based long-term, short-term memory architecture is used in well-known artificial neural network architecture. And this was chosen for time series prediction. That means the LSTM network is able to predict a time-dependent variable X. That can be the system observable infection rate or infection cases for a future sample point, for example, 4 weeks in the future, by past data. This is shown here again. Okay, here I want to show a case study, the well-known pandemic outbreak with the name COVID-19. It's 2 years ago that this pandemic situation arises in 2019, and the goal here is future prediction of system observables, in this case the infection rate or infection cases, from past data with a machine model trained with real and simulation data. This is a very challenging goal. Maybe it's not really possible with a high accuracy, because the real world has a very high variance and very different conditions, environmental conditions, and so on. And it's maybe like a weather forecast or a stock exchange forecast. But pandemic outbreaks or pandemic situations are a very good example where you can see that the real world data, the population data that is collected poses a very high bias, distortion, inaccuracy, and so on, and over time varying test strategies and so on. And so the data you get in the real world is more or less unused or useless. Yeah, so developing time series prediction models for pandemic observables from population data on a long-term timescale is nearly impossible just by using the real-world data. So, and the main issue already explained is the high bias and distortion of sampled population data. We are using official data available from the Robert Koch Institute, and really this database is mostly useless. And it's very difficult to calibrate the sensors. And so we go into simulation world, and there are different situations. Here again, this is Germany, and this is the partition of Germany on a two-dimensional Cartesian landscape of terrestrial units, basically towns and larger areas around towns. So we have in total 38 terrestrial units, and each domain is handled separately. This is important, by an agent. And we perform modeling, this training of the predictive model, for each domain. This is important to know. Finally, we can do model fusion, global model fusion, to merge again all the local models to get a global model. But it is not a part of this work here. We are just concentrating here on the single terrestrial units here. For example, Bremen, Hamburg, Schleswig-Holstein, and so on. Here we have maybe Munich, I'm not sure. So we have, for each terrestrial unit, we have an agent, and we perform here probabilistic, context-based cellular automata simulation to train an artificial neural network to perform the prediction of the observable infection rate or infection case. Okay, so here's a snapshot of a cellular automata simulation. Each cell can represent a place where a human can be. These are the green marked cells, so the cells are not portable. They pose no mobility, but the cell state represents a human that interacts with our humans. And you see here, these states are mobile in this cellular automata world. And it's very simplified, of course, but we have different areas: home, outside, work, shopping, school, culture, sports, and so on, with different interaction patterns and different interaction parameters. And we use digital twin methodologies to introduce a variance in the behavior of humans here in this simulation. So here are the first results, and this is not a simulation. The results level 1 are the prediction on population data. That means actually we have no simulation anymore. So we have only the aim of the time series prediction by a machine learning LSTM model trained with population data collected by the Robert Koch Institute from an infection database for the COVID-19 virus infections. Time range was about 52 weeks and partitioned in the already mentioned 38 terrestrial units and split it in 5 years age intervals of the people. So we use this data, and so we have 38 models, each one for each terrestrial unit. And the evaluation strategy is first training of the model in one specific terrestrial unit over the full longitudinal range. That means over full 52 weeks. Then the application to this trained model to the full longitudinal range. That means we're performing a playback from the beginning, and to evaluate what's the accuracy. Then we train the model only with part of the data, for example, the first 40 weeks. And then we apply again this partially trained model to the entire 52 weeks, to the entire 52 weeks longitudinal range. That means we perform a full playback. Yeah, and then finally we apply a model trained for an for one terrestrial unit to another terrestrial unit. And we want to see what is happening. First of all, here you see full range training over 52 weeks. Here partition in 4 age ranges from 0 to 9 years, 10 to 19, 20 to 59, and 60 to 99. And here you see the red curve is the original data with oscillation that has no cause in nature or biological reasons. This is the cause in the high distortion and bias of sampling. Here are the weekends, for example, where no data is submitted to the Robert Koch Institute and so on. Here you see the real world data has a very low quality. But what we see is here the blue curves. If we perform full training over all range of the full range and then go back to the start and perform a playback prediction, and the prediction is 4 weeks ahead, and this means the blue curve is shifted 4 weeks to the left, yeah? And we see a high accuracy. It's great. It's the terrestrial unit Bremen, and it's really amazing to see that the blue curve matches the red curve. Of course, it's an average, but it's really amazingly to see such a good accuracy. We never expect that. So we can predict in a playback, of course, the entire development over 52 weeks of the infection case number of the terrestrial unit Bremen. But now, if we apply, you see it here, if we only train the first 40 weeks, and then we want to try the real future, an unknown future, the model is more or less useless. You see here, the blue curve divergence. Of course, the near future can be forecasted, yeah, like a weather forecast, but the far away future can't be forecasted. It tends to oscillation and so on. So this is not a successful training. And here you see the application of the Bremen model to another terrestrial unit, fully trained, with a playback, and again the blue curve totally disagree with the real world development. And that means that one model of one terrestrial unit can't be applied actually to another terrestrial unit. There are main differences that can't be covered by the population data we have sampled or we have got from the official databases. Okay, now we're going to simulation. We perform a simulation with about 500 to 1000 cell agents per terrestrial unit. The agent behavior, mobility, interaction, health state, and so on is given by an average standard model and by individual behavior or by digital twin creation. And here we measure the infection case observable, or the infection case rate observable. And here you see a total different view. Of course, first of all, you see that here on the left side, the model is trained again over the full range. And here we have 2 infection wave cycles, very smooth. This is typical for simulation. No oscillations, of course, by the sensor here of the infection case observation of the entire terrestrial unit world. But if, of course, it's definitely smoother as expected. But if we train only a part of the time series, here approximately to the half of the entire simulation, and then perform again the playback, then we can predict. Of course, it's very similar to the first wave. It's not very surprising, but it shows we can train a model partially and can predict the far future. Here the the blue curve is very close to the red curve. So here we are able to predict the far future by simulation data. To conclude, prediction of time-dependent population observables from domestical official population data mostly fails to uncalibrated and distorted sensors. Simulation of large-scale populations, like in pandemic situation, is a challenge due to high number of entities and high degree of domain-dependent and individual behavior variances. typically not covered. Digital twin concepts, not here shown in this presentation, but used, can improve simulation by introducing micro-level variance, very important, micro-level behavior variance. Surrogate modeling by using simulation data. Replace computational complex agent-based simulation. Here, the surrogate model was a very small neural network with about 10 LSTM cells. It's very small neural network, can be computed by any microcontroller in your watch, for example, in your smartphone. And so this computational efficient, less computational effort efficient model can be used to replace the, here I show it again, this complex simulation of thousands of single agents. Okay, and a hybrid simulation model of agent-based and probabilistic context-based cellular automata methodologies is a good trade-off, and special domain partition is recommended and can further improve prediction accuracy, as you have seen. One model of one terrestrial domain can be applied to another terrestrial domain. Okay, so I'm at the end of my presentation, and questions and comments are welcome. And don't hesitate to contact me via the email. And thank you for your attention. Any questions are welcome.